After studying the concept of the two basic fundamental theorem, one was the Gauss divergence theorem that provide the relationship about the closed surface integral E dot ds and the open this volume integral divergence of the electric field from closed surface to volume integral 2 dimension to 3 dimension also you can say. So this was the relationship basically between the integral and differential form, and also surface integral is equal to the volume integral into this sense. And you can say that measurement of the electric flux throughout the surface and within the volume, that will remain same, that will be not change. So conversion from integral to the differential form also integrate. So if you want to convert this integral form E dot ds into the differential form, you can use this way. Divergence of the electric field basically gives the information about the magnitude of electric field at a particular point, the amount of electric flux, or if you are using it on magnetic field, then it will provide the amount of magnetic flux. So this was the first fundamental theorem of the divergence, known as Gauss divergence theorem. And then after you have seen the second theorem of the curl, known as Stokes theorem. This provides the relationship between the closed path integral of E dot dl is equal to open surface integral del cross E dot ds, curl of the field. So this provides the relationship between the closed path integral and open surface integral. This is the one dimensional to the two dimensional, one dimensional to the two dimensional. So it states that line integral of any vector field around any closed loop is equal to the surface integral of the curl of the same field over the total surface. Now basically what we have to do with these two mathematical statements, two theorems, this mathematical statement, with the help of this statement we have to convert integral formulae of the Gauss law in electrostatics, Gauss law in magnetism, Faraday law and the Ampere's law. Basically we have to convert those integral formulae into the differential form. First we will convert Gauss law in electrostatic into the differential form. From this law we know that this is closed surface integral E dot ds, this is closed surface integral E dot ds is equal to Q, that is enclosed by the surface, upon epsilon naught. So we have to convert this equation into the differential form with the help of earlier two mathematical statements. One was the Gauss divergence theorem. So Gauss law in electrostatics. Gauss law in electrostatics, you have seen into the first slide that it states that E dot ds is equal to Q, that is total charge enclosed by this closed surface, upon epsilon naught. Now here what we have to do to convert this integral equation into the differential form, for that I have to use Gauss divergence theorem. So using Gauss divergence theorem, so you have seen the formula of this is same. Closed surface integral E dot ds is equal to volume integral divergence of E dv. So instead of this left hand side, I can write directly volume integral divergence of E dv, and into the right hand side same as it is upon epsilon naught. But what is the problem here? Left hand side I have converted into the differential form, but right hand side is not comparable. So 1 upon epsilon naught is constant, so I have to convert this Q in terms of the volume charge density, because I know that in case of Gauss law, this was the sphere, and the sphere is solid, so charge is uniformly distributed, I can suppose. So that will be volume charge density into that. So I have to convert this Q into volume charge density, that is rho dV. So within the total volume of the sphere, total charge is defined in terms of the rho. So Q is equal to volume integral rho dV. This is rho, volume charge density. Volume charge density. So instead of Q, now I can write this. So this is your divergence of E dV is equal to 1 upon epsilon naught, and this formula of Q rho dV. Rho is the volume charge density that is constant into that sphere, so comes out from this integration and becomes rho upon epsilon naught and this volume integral dV. So now into the left hand side, you see this is volume integral, into the right hand side this is also volume integral, so both sides are comparable. So divergence of E dV into the left hand side, I can write this into this way, keeping together right hand side. So this divergence of E minus this rho upon epsilon naught dV is equal to 0. From this, now we have to conclude that there are two vectors, one is this one and second is related to the volume. I know the volume of the sphere could not be 0, so volume of this could not be 0, but so this vector might be 0. If this is equal to 0, del dot E minus rho upon epsilon naught is equal to 0. If this is equal to 0, then we can conclude del dot E is equal to rho upon epsilon naught. So this is our first result. We can convert this integral equation into the differential form with the help of Gauss divergence theorem statement. This is the use of mathematically for the mathematical development. Closed surface integral E dot ds is equal to Q enclosed upon epsilon naught in terms of the differential form is del dot E is equal to rho upon epsilon naught, where rho is the volume charge density. So this was the conversion of Gauss law into the differential form. Now the second law is Gauss law in magnetism. On the same way we can write that, because Gauss law in magnetism is closed surface integral B dot ds is equal to 0. So now again we can use the Gauss divergence theorem, and as a result we can say that using the Gauss divergence theorem, I can write here that mathematical statement directly. So this left hand side becomes divergence of B dV is equal to 0. So again, either this factor is equal to 0 or this factor is equal to 0. So volume could not be 0. That's why del dot B is equal to 0. This is second differential equation. We correspond to this law, which is known as the Gauss law in magnetism. Now what is the meaning of this del dot B is equal to 0? Divergence of the magnetic field is equal to 0. We have seen earlier that when we were discussing about the divergence of any vector field function and that result comes out 0, what will be the conclusion of that equation? For that we have had considered a open circle, open surface that is enclosed by this closed loop. The electric flux enter from one surface is equal in amount at the second end. So total electric flux is equal to 0. So here we can say what will be our conclusion at this equation, that monopole does not exist. Del dot B is equal to 0. If this flux enter through this open surface, it reaches basically up to the negative charge. It starts from the positive charge and reach up to the negative charge. So on the basis of this equation, when divergence of B is equal to 0, it means that monopole does not exist. Magnetic pole, a single magnetic pole could not be possible. So a meaning of this equation is monopole does not exist. So this is the meaning of second equation, and this is the differential form of the equation. Now the Ampere circuital law. This is a current carrying conductor. I current is flowing. So as a result, this magnetic field develops circular. These are the magnetic fields, circle like this one. So Ampere's circuital law states that the line integral of any magnetic field around any closed loop enclosing a current I is equal to mu naught times the total current. It means B dot dl is equal to mu naught times I. That I current is enclosed by that loop. So this is closed path integral indicate to this one B dot dl is equal to mu naught I. Now we have to convert this integration form into the differential form. So from the Stokes theorem we know that closed path integral E dot dl. So closed path integral E dot dl is equal to open surface integral and this curl of E dot ds. So now we have to use this theorem to convert Ampere's circuital law into the differential form. But before that, one more important formula for the current, that is J dot ds. Because in case of Stokes theorem we have seen here the open surface into the right hand side. So when we will use that Stokes theorem into the left hand side, we will get this situation, this open surface integral del cross B dot ds. But into the right hand side we have mu naught I. So we want surface integral into the right hand side. So we have to convert this I into the open surface integral with this formula. So now put this value of I here. So B dot dl becomes this open surface del cross B dot ds with the help of Stokes theorem, and the right hand side mu naught I put the value of I from here, it becomes mu naught times open surface integral j dot ds. Now you can compare both the side. So J is the current density that comes out, that is constant basically, into this current carrying conductor and comes out from this integration. So mu naught times J. So del cross B minus this we know that this is comparable, so bring out this right hand side into the left hand side, it becomes minus. So del cross B, this one, minus mu naught times J, this factor, and dot ds is equal to 0. Now we have to conclude here that area of this open area developed by this closed loop is not 0. So the inner factor del cross B minus mu naught J, it could be 0, but it is real physical situation that this area is not 0, so we can say del cross B minus mu naught times J is equal to 0. So from this equation we can conclude that del cross B is equal to mu naught times J. So this is the differential form. This one is the differential form of the Ampere's law. Del cross B is equal to mu naught times J is the differential form. So now the last one and formula, that is known as the Faraday law. So Faraday law in Faraday law's law of electromagnetic induction, it states that whenever the magnetic flux linked with a coil is changed, an induced EMF is produced in the coil, and it will last as long as the change in the flux continues. So here we have shown that this is a coil. The EMF is directly proportional to the time rate of change of the magnetic flux. So when you pass a magnetic flux basically through a coil, in the coil electric EMF basically produced. That EMF is defined by this way: closed path integral E dot dl. This E dot dl is basically what? This is a potential. E dot d is equal to V. If you remember, this E dot d is equal to V. So that potential basically you are observing through the change into the magnetic flux that is linked with the coil. If you have this coil and you pass a magnetic field through this one, that is changing with respect to time, so an electric EMF will produce into this wire, that is known as Faraday law, and the current basically opposed to the change into the magnetic flux. So E, that is EMF, is equal to closed path integral E dot dl. E dot dl is related to this one, this closed loop, minus del phi by B upon del T, time rate of the magnetic flux. This one, if you will change the magnetic flux, there will be EMF. Now how to convert this integral form of the Faraday law into the differential form? For that we know that phi b is what? Phi b is the magnetic flux, and how to write that? That can be written as associated with the closed loop is B dot ds, magnetic flux. Here area is open, so phi b is equal to B dot ds according to the formula, that is this one. Now the E dot dl is equal to minus del phi b upon del t. That now put the value of phi b from here, you will get this B dot ds minus del upon del t B dot ds, and this becomes in this way. Now apply Stokes theorem into the right hand side. So this is closed path integral E dot dl, it becomes open surface integral del cross E dot ds, and into the right hand side this vector minus del upon del t. Now both the side you are observing open surface integral, so both are comparable, so you can write into this way: del cross E plus this minus sign becomes plus when you bring out the right hand side to the left, plus del b upon del t dot ds is equal to 0. Again area could not be 0 whether that is open or closed. So but right now the surface is open, this is open surface, and this is closed loop, this is basically a coil, this is wire. So now area could not be 0, so this vector del cross E plus del B upon del T is equal to 0. Del cross E plus del B upon del T is equal to 0, and hence del cross E is equal to minus del B upon del T. So this result, this equation is the result into the differential form of the Faraday law. So now we have 4 equations into the differential form and integral form. So these equations are known as Maxwell equation. The first differential form, these are the first one, del dot E is equal to rho upon epsilon naught. Second is del dot B is equal to 0. Third is Faraday law, that is del cross E is equal to minus del B upon del T. Fourth is Ampere's law, that is del cross B is equal to mu naught times J. J is the current density. So these are the 4 differential equations correspond to the first law, E dot ds is equal to Q upon epsilon naught. This is integral form, this is the differential form of the first law. Second is closed surface integral, B dot ds is equal to 0. Third is the Faraday law, EMF is equal to closed path integral E dot dl is equal to minus del phi b upon del t. Fourth is Ampere's law, that is state closed path integral B dot dl is equal to mu naught times I that current is enclosed by this closed loop. So these are the integral form and the differential form, and these equations are very important into the electrodynamics and known as Maxwell's equations, Maxwell 4 equations into the electrodynamics. Basically these equations are the result of the connection between electric field and magnetic fields. And so now after that we will study about the continuity equation